All right. In the last video, we made preliminary images of 3 star clusters: a young open cluster, an intermediate age open cluster, and an old globular cluster. But we didn't stop there. We took some measurements. We extracted many of the stars in the images, and we measured their brightnesses in 4 different filters: B, V, R, and I. So we took a lot of measurements and we downloaded these measurements as a CSV file. So in this video, in the videos to come, we're going to use these measurements to dissect these clusters, figure out what makes them tick, do some science. We are going to figure out, why are the stars the brightnesses that we measure? Why are they the colors that we measure? I told you that one cluster is young, one is intermediate age, and one is old. How do we know that? You're going to measure the ages yourself. The metallicity of the gas that made the stars, the amount of dust between us and the star cluster, and the distance to the star cluster. We're going to learn how to measure all these things. Okay. So to get started, you need to go to this page. This is the Cluster Astromancer tool, or sometimes called the Clustermancer tool. It's part of our Astromancer suite of tools, and you can find them at astromancer.skynet.unc.edu, and then select the cluster tool from the list on the left, and that will take you here to Cluster Astromancer or Clustermancer. Okay, this is relatively new. We're still debugging it a little bit, but I'll show you how it works. First step is to upload one of your data sets into it. Let's start with your young open cluster. The globular clusters are farther away. We can't see the fainter stars. It makes it harder to analyze, makes them harder to model. So let's cut our teeth on the open clusters. They're a little bit easier to do. So come over here to the left and upload your CSV file. And then you need to type in the name of your cluster. Mine is NGC 2437. I hit next. And what it's doing is it's cross-correlating your list of stars with the Gaia archive. I'll tell you more about Gaia in just a moment. The Gaia is a space mission that's observed many, many stars in our part of the galaxy and has measured not just their brightnesses, but a few other very useful things about them: their distances and their motions across the sky. And we're going to make use of that in just a moment. So we need to match up these catalogs. Didn't take very long. I uploaded 3155 stars, 3,155. It found 2749 matches. So we're going to focus on those 2749 stars. We'll hit next, and this will take us to the field star removal page. So, field star removal. Let me start by showing you a picture of my cluster. So this is NGC 2437. It's an open cluster. This one, I didn't actually make it. A colleague of mine made it, but he stacked more than 5 images. So this goes deeper than the ones that you're doing in this module. So that brings out more stars and makes it look a little bit prettier, but the procedure's the same. Now, one thing about these images is not all the stars are tied to the cluster. You have the cluster stars in there, but you have some unrelated stars, stars that are much closer to us than the cluster, or stars that are much farther away. these unrelated stars are called field stars. And especially with the open clusters, most of the stars in your image are field stars, unrelated to the cluster. And they're just going to mess us up. If we're trying to study the cluster, we want to get rid of as many field stars as possible. The open clusters are in the plane of the galaxy. And so that's why we're picking up all these unrelated stars. The globular clusters are up above the plane of the galaxy. And so when we look at them, we're not looking through as much of the regular galaxy, and so we don't have as many field stars. Globular clusters will still have some, and we'll want to remove them. But the open clusters have a lot, and we need to remove them. Now, how can you tell which of the stars in this image belong to the cluster and which don't? Well, the key thing to remember is that cluster stars are born together. It starts out as a giant cloud of gas. That cloud gets disturbed. There are all sorts of reasons why a cloud can get disturbed. And once it does get disturbed, it starts to collapse. And as it collapses, it fragments. And the fragments fragment, and those fragments fragment until you have a whole bunch of little fragments. And each fragment forms a star system, a solar system. Some of them are single stars, some are double stars. Probably most of them have planets. Okay, so that's how they're formed. And the thing is, since they all form from the same cloud, they're all going to be the same distance away from us, pretty close to the same distance away. And even more importantly, they're all moving together. That cloud, before it collapsed, was moving across the sky at a certain rate. And as it collapsed and formed all the stars, now all those stars are still moving across the sky at that common rate. So the cluster members are all traveling together. The field stars, most of them are traveling on other trajectories. Okay, we're going to use this and use the differing distances to separate out the cluster stars and get rid of the field stars. Okay, for that, we're going to make use of the Gaia data. We've already cross-correlated with Gaia. Here's a picture of Gaia. Gaia is a European spacecraft, European Space Agency, put up in, I think, 2013. And it's just been remarkable and revolutionary for astronomy. It's measured the distances to a great many stars using a technique called parallax. Okay. So here's how it works. Gaia stays close to the Earth, and as Earth orbits the sun, Gaia orbits the sun. So imagine, let's say we're here in January, and Gaia is trying to measure the distance to this star. It takes a picture, and it sees the star over here with these more distant background stars. 6 months later, we're on the other side of the sun, looking from a different point of view. And we look at this nearby star, and it's now over here, around these background stars. It appeared to shift just a little bit. The nearby stars, the very closest stars, can shift, a fraction of an arc second. The far away stars, you're talking milli-arc seconds. Very, very small shifts, but the spacecraft is good enough it can measure it. And once you know the shift, you can calculate the distance. For example, here's a star, and it has a certain shift from here to here. Here's a closer star, it will be a bigger shift. So the amount of parallax gives you the distance. Now, I should say, these figures are not to scale. There's no nearby star this close to us. We'd be a binary system. We'd see another sun in our sky. All the stars are very, very far away. So this is not to scale, but you get the idea. And to think of it another way, it's the exact same technique surveyors use. You've seen surveyors out, they have their tripod, they're looking through making a measurement of something kind of far away. Then they move their tripod to a different observing location, and observe it from a different angle, and then do this calculation to figure out the distance to the thing that they're surveying. Okay. This shows you the range of Gaia. The mission before Gaia was called Hipparcos, and it just did a tiny, tiny part of the galaxy very close to us. Gaia is more powerful, and its observed distances all the way out to here, going past the center of the galaxy. It's not, we don't have the whole galaxy. We don't have distances to stars to the whole galaxy, but we now have them to a big chunk of the galaxy, which is really useful. The other thing Gaia's done, since it's been observing for so long, and it can measure stellar position so precisely, it can see the stars moving across the sky. They do move very slowly. Nothing you'd see with the human eye, but milli-arc seconds. And it's measured that, and we can make use of that because, as I said, stars that are born together travel together. And this motion across the sky has now been measured. Okay. So here we are on the field star removal page. Let me show you what we have. The top row is all proper motion. So here's a histogram of how many milli-arc seconds per year each star is drifting. And most of the stars, you have some kind of distribution, but there's clearly a peak here. That's the cluster. They're all traveling kind of together. And that's the motion in right ascension. Here's the motion in declination. Again, you have a peak. And in this middle plot, we have a scatter plot showing the proper motion in right ascension on the x-axis, the proper motion in declination on the y-axis. Now, it's important to note, this is not a picture on the sky. This is in motion space. Here you can see the cluster. They are all moving in right ascension, in declination, kind of with the same proper motions, where the other stars are all over the place. So we're going to now separate out the field stars from the cluster stars, or the cluster stars from the field stars. So go to the bottom slider on either histogram and isolate the concentration. See how we've isolated in right ascension, and now I'm going to isolate it in declination. Okay, so I've kind of circled the cluster stars, and the field stars have now changed color to purple. So next, let's zoom in, and that's what these upper sliders do. Zoom in so we have a better view. Now I'm going to show you a common problem. If you go too far, you cut into the distribution. If you back out, you lost them. If you go too far, it pushes the lower slider. If you do that, don't worry, just come down here and reset the lower slider. I'm going to zoom in on this axis too. And then once you zoom in, you can fine tune it a little bit. Okay, so I've circled the cluster stars, and everything outside I'm treating as a field star, an unrelated star. You can see we've already removed 67.7% of the stars in our image. Last thing we're going to do is isolate in distance. There could be some stars that have the same motion across the sky as the cluster stars, but just by chance, they're actually much closer or much farther away. And so we can remove those down here. So here's what we want. I'm going to zoom into that distribution first. The open clusters that we'll be studying, they're all pretty close to us. The globular clusters are far away. This is an open cluster, so I had to zoom way in. And in fact, if the the slider circles get too close together, you can edit it manually. I'll show you that in the text boxes. Something like that. Then I'm gonna crop it here in distance. And if you come back up to the proper motion plot and hover over the word field star, you can now see those purple stars in the ellipse? They have the same proper motion as the cluster, but they're not cluster members. Those are the ones that were too close or too far that we just cut out. And they look to be about the same density as the stars around it, so we did a good job. If you see an overdensity here, you cut out too many. And some of those are cluster members, and you want to put them back by expanding this range. So now we're up to 69.4% of stars removed. And again, that's just with this cluster. Each cluster will be different. Okay, so we've gotten rid of the junk, and all that's left are cluster stars. We have a nice, clean color magnitude diagram. It's kind of like an HR diagram, but learn about that in the next video.